Yes, welcome to this session, a summary key point on CNC threading and grooving guide. I want to just give you a summary key point. When you're doing grooving and also when you're doing threading, what factors do you consider for either Fanuc machine, Siemens machine, or other ISO machines for creating a program? CNC threading and grooving, the key areas you need to look at. Common G code for threading may be different. You also need to understand the form. If you're doing cylindrical, taper, or face threading, you need to understand the format and the structure of the threading cycles. You need to also understand how to create a program, and then the conversion between the pitch, millimeter, and also TPI table. I'll give you a table, and then a complete operation for each of the guide. So this guide is relevant for CNC programmers, machinists, students, engineers, and trainers who are venturing into CNC subtractive machining. Normally, the benefit of understanding CNC threading and also grooving will help you to universally be able to understand the compatibility of different machine controllers like Fanuc, Siemens, HAS, GSK, HNC, Star, and whatever. Then also it will help you to understand the practical examples for each of the block, safety guidelines, and also the best procedure of applying threading and grooving, conversion table between the metric and TPI. Then we'll create an example of each of the programs so they were able to understand how it can move across. So in this session, our main aim is to understand the relationship between grooving and threading and how you can create a program for each one of them. So let's start with the first one. For threading, you understand some of the G code that are used across. I may not have put all the G codes. For example, we have G32. This is normally used for single line threading. It's synchronized in such a way that the feed is well synchronized with the machine. It's normally used for manual control thread and also simple operations. You can also use what you call G33. G33 is a thread cutting cycle with the constant lead. You can use it for thread cutting. I'll show you how to create a program for each of one of them. It's almost similar to G32. And then we have G76. This is a multi-pass compound in infinite threading cycle, which is most common and efficient threading cycle. Then we have another code which you call G92. This is a simple threading cycle. Most of the old machines were using this for basic threading, and then the current one, some of them are using the G82, like the HNC, Star using G82. Then G96 and G is just ensuring that the speed or surface speed you're using is constant, so that you maintain the surface speed for consistency. Then you have G97. This one, you are telling the machine that you cancel the constant cutting speed, constant surface speed, whereby now you can rely on RPM for thread operations. So in this case, we have to go one by one on some of the examples of the G code threading I've given you here. For example, the threading cycle format and structure. If you're using G32, as I said, is a single line threading where you just write like G32 X now the diameters, where the minimum diameters you are threading, then Z, the Z position where you want to thread up to, then F will represent the pitch. Normally F is normally equal to pitch, which means here we don't put the feed rate because the machine will be the spindle will synchronize the feed rate when you are doing threading, so you don't need to put the feed rate here. Then an example, like if you're doing, let's say, a pitch of 1.5 for internal thread, this is the code, this is the main code. For example, you can say put a constant speed of 600, then let the spindle speed rotate in the clockwise direction with the speed of 600, and then ensure that you position your tool to move close. Maybe, for example, if your diameter was, let's say, 24, you want to do M24 by 1.5, so you can bring it close, or let's say this M20 by 1.5, you have to bring it close. For example, G32, which means a safe point. Then Z2 is also safe point, just a safety part before you cut. Remember, a part program consists of the safety approach, the cutting body, and the safety retraction. So in this case, this is like the safety approach. So you are putting safety approach before you now start cutting the thread. This 1.5 becomes the pitch. If you are using G76, G76 is a 2-line threading cutting cycle, which can also be used in Fanuc or Siemens or Haas or even GSK. Like the first line, normally it has 2 lines. The first line, you normally write G76 P. P has MRA, then it has Q, which means Q is the minimum depth. Then it has R, which means that's the finish allowance. Then the second line of G76, you may find X having the minimum diameter, Z being the end position of the point where you want to thread up to. Then P can be the depth times the 100. Normally you put as whole numbers. Then Q on the second line for G76 can be the final depth. Then F is now the pitch. For example, this, I will show you an example, or let me explain the meaning of each one of them. As I said, from this you have the first line for G76 and this is the second line for G76. So the first line is about control parameters. Then the second line is now thread dimensions. You are putting out thread dimensions. So if you look at this example here, you have G76 as a threading cycle. The one in green, I'm putting semicolon behind, which means I'm letting the machine to jump. So you have G76, P01, P01, 20, 60, then Q150, R01. What does it mean? When I write P01, 1260, it means 01 is the finish pass. So my finish pass, I'm using 0.1 millimeter. Then 20 pull out the chamfer. You take the pitch times this 20, for example. You can get now the chamfer amount or the pull out. Then 60. This 60 is the angle. Normally for metric standard threading, we normally use angle 60 for thread. Which this is the last one, which means the tool is for angle. You're putting a thread with the tool of angle 60. Then Q150. This is the minimum depth you are going to use. The minimum depth you're going to use is now 150. You take 150 divided by 1000, you get 0.15 millimeter. Then R0.1, that is the minimum finishing allowance. So this is the first line. As I say, the first line is about the control parameters. Then the second line is about now the thread parameters. So this, for example, if you're doing a thread of M24 by 2, you have to find the minimum diameter. So the minimum diameter here will be 24 minus 2. So that's why you are writing here G76 X22. So it is X22, and then here you put now Z minus 30. For example, if you are cutting it, you're doing a thread up to Z, up to a point where it is it is maybe the length of the thread is 30. So because you're cutting towards the spindle, we're putting Z minus 30. Then you have 800. This 800, it means that's the thread depth. So you take 800 divided by 1000, you will get 0.8. So in real sense, it should be 0.8. But you're writing 800. Then Q300. 300 means now is the first cut depth. So it is 300 divided by 1000, because it is in microns. Divided by 1000, you get 0.3 millimeter. Then F is now the pitch. Now we place this as the pitch. So this is how you write the program for each one of them. As I had already explained here, the first line is about the parameter for the control parameter, and the second line is the thread parameters. So where you might find MRA. So the first two digit normally it represents the number of finished passes. Then the second 2 digit, which is now R, represents the pull out angle or a chamfer amount. Then the third pull out, the third parameter A, it has also 2 digits, represent the angle for the metric. If you are using metric, it's normally 60 degrees, but if you are using the maybe British system BSF, it can be 55 degrees. That is imperial. Then the Q is the minimum depth for the pass. Normally it is put in microns. Then R is the finishing allowance for the first line. Second line, it is talking about the thread parameter. So you put X as the minimum diameter. So you take measure diameter minus the pitch, you get the minimum diameter for the thread. Then Z, the thread end position. Pitch P is now the thread depth times 100. Then Q is the first cutting depth in microns. Then F is the thread pitch in minute. So this is how you write the program for G76. As you can see here, this is a program for G76. You are doing a cylindrical thread of M24 by 2. So you have to ensure that you have to put, first of all, the safety approach, ensuring that you use constant speed, can cancel any constant speed for this case, and then introduce now the first line. This is now the first line, then the second line. And then from there, you need to understand some of the key parameters. So there are different types of thread you can do. You can do what you call cylindrical thread. Either you can use G76. You can also do what you call taper thread. You can use G32 to do taper thread, which means you require also the points. Then you can also do what you call face thread, like doing the threading on the face. It's like radial threading. You can also use G32, can also be used to do face thread. For you to do the thread, always understand that if you are doing thread, do not use G76. Do not use G96, because G96 is a constant surface speed. So you need to use G97 to ensure that you're able to cancel any constant surface speed. Then ensure that you allow proper synchronization between the spindle and the feed. That's why here in threading you don't have the feed. You only put the pitch and the spindle. So the spindle will automatically synchronize itself in CNC turning. Then ensure that you use appropriate cutting fluid, because once you start threading, if you press stop, you already affecting the work. So ensure that before you press a cycle start, you have all checked the parameter that already there's enough cutting fluid, there's enough coolant, and you have done verify you have done simulation to ensure that the program is well catered for, and also you ensure that there's safety approach and safety traction before you start. You need to check these parameters when you're programming. This is for threading. We'll see how to create a program for G32 or G93. How can we create a program for G32 or G93? Let's look at it for grooving. What is in for grooving? Also grooving, you can either use G00 and G01 for grooving. I know G00 is rapid positioning, and then G01 is linear cutting. You can also use G01 for grooving, where you can do it manually. Even you can write a program for G01, it can do grooving. Then the cycle one for Ken cycle, you can use what you call G74 or G75. It may depend on the machine, so don't mix the code for a machine if the machine doesn't allow G74 or G75 for grooving. So G74 is normally for face grooving or axial grooving cycle. You are grooving on the face part, that is the Z direction. Or you can also groove using G75. That is or outer diameter or internal diameter radial peg grooving cycle. Can be used for external and internal radial grooving. Then you also ensure that you counter check if you are using G96 or G97. Types of grooving, as I said, we have OD grooving, that is outer diameter grooving or radial grooving, then inner diameter radial grooving, then we have axial grooving, and then lastly part off. So you can do these type of groovings: outer diameter radial grooving, inner diameter radial grooving, axial grooving, and part off. The main purpose of grooving is to ensure you are putting a snap ring or O-ring to prevent leakage. That's the purpose of grooving. Example of the format and structure for example G76, G74 for the face grooving or axial grooving cycle. You have to put the first line as G74 R. Then R is the amount of R you put is the retraction amount. Then the second line G74, you put X with the final diameter where you're grooving up to. Then Z, the final length of Z position where the tool should be. Then P, you're putting the depth times 1000 because you're converting from to micron. Then Q, the peg amount, then F is the feed. So in this case, for example, if you are doing a groove of 4mm depth, maybe on diameter 44. So how will it be? For example, I can say G97, spindle speed of 300, rotate spindle speed of 300 in the clockwise direction with 300. That is a constant spindle speed rotating in the clockwise direction. Then I have to position my tool maybe close to my diameter, because my diameter, the grooving maybe is, let's say it's 40, I can say 42, then Z is 2 or 1. Then now this G74, the first line, as I said, R is the radial amount, so it's a retraction amount. So retraction amount here is 0.2 after the peg. Then second line now, G74 again, X40, Z, X40, Z minus 4. So X40 meaning I'm grooving up to X40. Then Z minus 4, which means I'm moving my tool from 0.2 Z minus 4. So it will be grooving from Z minus 4 from the origin. So I need to know how to set. Then P 4000, that is 4000 divided by 1000, you get 4 mm, which means the depth of groove is 4 mm as per this. Then Q is 200, that is 200 divided by 1000, you get 0.2. That's the peg depth. Then lastly, F is the feed rate. So the feed rate here I'm using 0.15 or 0.1. That is the example of G74. Let's look at also example of G75. What does it entail? As I said, G75 can be used for OD or ID radial grooving cycle. So for OD grooving cycle, using R for the reduction amount for the first line for G75, and then second G75, X is the final depth, Z is the width end, this is the width end, then P you're using as the depth times 1000 meters because we're putting the microns, Q is the peg amount, and F is the feed. So in this case, an example, if you're using this, always I said a part program consists of the safety approach, the cutting body, and the safety traction. In this case now, I'm using a constant cutting speed of 450, but I'm telling the spindle speed to rotate clockwise in the clockwise direction. Then here, I'm approaching to a safety point where X is 50 and also Z is minus, for example, Z minus 10. So it is going to the point where I need to cut. So if I want to cut to 5 mm wide, and maybe I've put the groove is at 0.10, that is 10 by plus 5, you get minus 15. So I'll move to minus 15. But this is the first point I want to approach my tool, because these are just positioning my tool. Then the first line, which is 75, it is R 0.1, 0.2, which this is retraction after the peg. Then the second line, G75, X44. So which means I'm doing a groove up to diameter 44 as the final depth of grooving. Then Z minus 15, because my tool I had put at minus 10, so plus 5 of the width, I put what? Minus 15. Okay, this is direct. But if you are using a tool maybe of minus a tool of width of 3, so I can put minus 13 here. Yes, minus 13. Then I can be changing like that. Then you have P 3000. That is 3000 divided by 1000. I get 3. So which means the depth of grooving is 3 mm. These are in microns. These are in microns. Then Q is the peg depth, which means that is 200 divided by 1000. I get 0.2. Then lastly, F is the feed rate. So the feed rate I'm using 0.112 per, that is millimeter per revolution. So this is the format and the structure for G75. So there are various parameters you also need to consider. Also the material if you're programming. If you're using mild steel, you need to use the cutting speed between the spindle speed between 150 to 120 to 150 with a feed rate of 0.08 to 0.18. Coolant must be always be there. If you're using stainless steel, you can use spindle speed of 70 to 100 with a feed rate of 0.06 to 0.01 if you're doing grooving. If you're using aluminium, you can use a spindle speed of 180 to 300 with a feed rate of 0.12 to 0.25. If you're using brass, you can use a spindle speed of between 200 to 350 with a fit rate of 0.1 to 0.22. So you need to ensure the cutting parameters for each material, and also you calculate, because there's a formula you can use to calculate. This is an example of maybe of the depth for safety. You are using maybe a tool with a depth, a grooving tool with a width of 1.5. The safety approach for the groove should be 2 millimeter. If you are using 2 millimeter for the width of the groove, it should be 3. So this is a simple chart. So when you're using grooving, the best practice you can observe is ensure that the peg for G74 and G75 are used for deep grooving to break the chips. For parting off, you can reduce the fit and then use G01. Always use sharp insert. So the sharp insert, normally don't use a radius insert unless you're doing a radius groove. But if you're using you're doing a sharp groove, use sharp insert with the radius of either 0.1 or 0.2. Then also consider the groove width. Check the groove width. Here I'm putting an example, but you need to check the groove width size so that you match the point where you are going to align for the Z. Then also for internal grooving, ensure the adequate clearance so that the tool is able to allow chips to move out. At the same time, when the tool is retracting, it is not obstructed. That is how you understand the grooving. So let's go to the conversion. I also put a conversion, for example. If you want to convert from pitch to TPI, how do you do it? This is my formula. If I put 2, then click calculate, it will give me 12.7. That is TPI. If, for example, I put, let's say, 8, then I say calculate, give me a pitch of 3.175. Or if I put a pitch TPI of 20, then I say calculate, it give me a pitch of 1.227. These are correct values. How do we do it? Let's go to the formula. So this is how to convert from pitch to in pitch in millimeter to TPI. TPI means tooth per inch or thread per inch. So let's go to a formula here. If you are converting the pitch from millimeter to TPI, you take 25.4 divided by the pitch in millimeter. For example, a pitch of 1.5 millimeter, you take 25.4 divided by 1.5, you get 16.9. Let's come here on our formula here. I want to convert from 1.5 millimeter to TPI. What value do I get? I write here 1.5. Then I click calculate. It will give me 16.93. So this is the formula that is there to calculate to change or to convert from pitch in millimeter to TPI in inches, or the pitch in inches. Then if you are converting from TPI to pitch now in millimeter, you take now 25.4 divided by the TPI. For example, a TPI of 16, I want it to convert to millimeter, pitch in millimeter. So I'll take 25.4 divided by 16. I get what? 1.5875. Let's confirm this. Let me write here a TPI of 16. What value do I get? Then I say calculate. You see, I get a pitch of 1.657. So normally close to millimeter, it may take a pitch of 1.5. Okay, let's look at a simple reference table. If you have a pitch of 0.5 millimeter, the TPI is 50.8. That's fine thread. If you have a pitch of 0.75, you may get a TPI of 33.9, also fine thread, like that. So this is an example of a chart I've prepared, so that when you are doing the threading, maybe conversion, you need to understand how to convert from TPI to inches. I know Africa we normally use millimeters, but the US you normally use inches. So when you are working, you need to know how to convert so that you give the best output for the thread. Also, you can convert from TPI to pitch in millimeter, and the common thread. For example, a TPI of 8 is close to 3.175 pitch, or a TPI of 10 close to 2.54, a TPI of 11, 2.31, 12, 2.11, like that. So you need to know how to relate. So when you're designing and you're machining, refer to a design catalog or a machine manual or programming manual or the design manual. An example of this, just a simple, we normally know that 25.4 millimeter equal to 1 inch. That is the exact conversion factor you can use. Metric threads are normally specified by the pitch in millimeter, but imperial threads are normally specified by TPI, thread per inch. For accuracy in programming, use exact calculated values. Most common approximations are acceptable for manual setups. So this is the key part you need to consider when doing threading. So this is a table for threading. Conversion from between TPI to pitch in millimeter and pitch in millimeter to TPI. Let's look at the example of a program. I've just made a simple program. I'm doing an external threading using G76 on M16 by 2, which means M is metric, 16 is the major diameter, and 2 is the pitch. That's the meaning of this. So M16 by 2 external threading, I'm cutting to a length of 25. I'm doing a thread to a length of 25 millimeter. So how do I write a program? For example, I can write 0 or with 4-digit number. If you're using GSK, Fanuc or Haas, I can write 4-digit number, that's the program number. Then I can write G21, G40, G99. G21, I'm telling that machine I'm using metric system. G40, I'm cancelling end tool nose radius composition. Then G99, my feed rate is in revolution per millimeter. And I can use G94 or G95 depending on the machine. Then G50, I'm telling my machine that the maximum speed is 1200. But if you're using Siemens, you don't use G50, you use LIMS, limiting maximum speed equal to 1200. Then here I can say G97, now constant speed, spinner speed of 450 in the clockwise direction. Then now my tool, I'm telling the machine I now start the tool, select the threading tool number 1 at offset 1, T01, 01, tool number 1, offset 1. Then now, because I'm using, I want now to position my tool, the diameter here is 16, but I'm positioning my tool to 18. There is a safety of 2 millimeter away from the workpiece. Also, if I've set my workpiece to 0, now I'm putting it away. Now this is what we call safety approach. This part is what we call safety approach in our program. Then from there we can now start now using G76. As I said, G76 so for cycle threading, I can put G76 P01 20 60 Q120 R0.01. What I said it means this is for control parameters. The first G76 line is the control parameters, which means P01, that is 01 is the finish pass, 20 is the pull out, that is the chamfer amount. We take the chamfer amount times the pitch. Then 60 is the angle, because I'm using metric, so my angle is 60. Then Q, this is the minimum depth of cut, that is 120 divided by 1000, I get 0.12 millimeter. Then R is the final finish allowance of 0.05 millimeter. That is for first line for G76. Second line, I can now write minimum diameter. So I take 16 minus 2, I get 14. So my minimum diameter for the thread is 14. And then I'm cutting to 25 millimeter. So I put here 25 millimeter, Z minus 25. Then for P400. P400 is the thread depth. So it is 400 divided by 1000, get 0.4 millimeter. Because they are in microns. Remember this one in microns. Q200 also in microns. So it is 200 divided by 1000, get 0.2 millimeter. Then the pitch is now 2 millimeter. As I said, M to 16 by 2. M is metric, 16 is major diameter, 2 is the pitch. Then once I finish, I have to retract, move away now to G00, X100, Z100, trap it to save position, then stop the spindle, restart and rewind. This is a program for G76. What about if you're using G76, for example, on maybe M30 by 3.5 internal grooving, internal threading. The internal threading also, maybe my program number is now O, then 4-digit number, G21, G40, G99. This G99, other machine can use G74 or G94 or G95, depending on your machine. Then G97, my constant threading speed is 300 in the clockwise direction. Number two for internal threading. And then 34. Remember this one you don't need to put 34. It is internal. So how do you put the safety? It should be 34 minus, because now the hole, what is the hole inside? you need to make to drill to a diameter of 30 minus 3.5, which is close to 20. This is not to be should not be 30. So don't you follow this 34 and 30. Here I need to change these parameters. So it should be 30 minus 3.5 for the minimum, because it is internal safety approach. Then yes, this is okay because it's away. It's okay. Then when I start the first line, P001 2060, same applies. It has the same chamfer 60 and the angle for the thread 100. Now the depth. So the minimum depth of cut of the threading is 0.1. Then finishing allowance 0.1 millimeter also. Then the second line for G76. So here don't put 30 because this is internal. So internal, which means it should have you should expand up to 30. So it is 30 minus 3.5, which is 26.5. So I have to put here 26.5. Then Z minus 40 because I'm cutting to a length of 40. Then P 1200. That is 1200 by 4000. I get 1.2. That is because 1200 is in microns. So the thread depth is 1.2 millimeter. Then Q 500 in microns. It will be 500 by 1000. I get 0.5 for the final cut depth. Then pitch is 3.5. Then from there retract, move away to a safe point, which means this one should not be 100. Also, this one should be 26 point. I can put 24 point or 25 millimeter. I can put 25 millimeter X and then Z away, because this is very important. I've put this one so that you understand the safety retraction in the internal threading. Remember, it is internal threading. So here it should be at different values. Let me show you this value. Let me show you this value. Can use an example. Example here. Let me put this value here. So this value for internal is not supposed to be this. So you need to put 26.5, or let me 25. We can put here 25. It's okay. 25. Then when it is moving away, also here you have to put 25. Yes. Sorry, not 1.5, 25, because it is internal. Yes, it is internal. These values are internal. So this you need to know how to put these values because it is internal. Okay. Let me put somewhere here. Put somewhere here. Can you put it here so that you can see it? Let me put here. You see, this is internal. So you don't put 34 here. Even this one should be 26.5. That's the minimum diameter for the threading. Because sorry, this one is okay because you are coming from 20. You are coming from 26.5 to 30. Because now internal expanding it. You are expanding it. That is how you do for internal. Then when you come to face threading, for example, you can also do face threading. An example of face threading using the same example G32. So for G32, you can either use G32 or G33. So here you are putting X25 is the diameter now. The diameter you are doing threading, for example, where you want to do face threading. Then F1.25 is the pitch. Then once you finish, because it's not a cane cycle, it's a single block. So you need to put a safety block for retraction so that it moves to a point of safety. Then from there it comes back to that point of cutting of threading. Remember, this is why I'm only using X10 because it is on the face. I'm maintaining X. There's no Z here. The Z is 0. Check here. The Z is 0. So I'm maintaining other values, but X is rapid positioning to the back of the diameter so that I start again and then come to another diameter. So I'm expanding it. X25, then X28, then from there I can go to X30. That is an example for face threading. What about grooving? I think we had already written a program for grooving. For example, if you're using grooving, in this case, I'm only interested in these parameters. We are using G75 for grooving. So the first line for G75 is the retraction amount. So after each peg, then second line I'm putting 50. So it is 50 diameter where I'm grooving it to 50. That's the minimum diameter. I'm grooving it. Then Z minus 25. Where am I grooving? With the point of grooving, I have to move my tool to where Z minus 25 is, which means I'm compensating maybe by 5. That is 20 plus 5. I get minus 25. Minus just the direction along towards the spindle, towards the spindle. Then P5000. It is 5,000 divided by 1,000. So which means my depth of cut is 5. But you don't need to put the full depth of cut. You can put maybe 2, first of all, 3 like that. I can put 2,000, 3,000 like that. So that I go in steps. So this one I have put all of it. I can go also in steps. Then Q300, that is 300 by 1,000, I get 0.13 millimeter for the peg. Then the filtered is 0.12 millimeter. Then I move away from that, and then I go to retraction. Then we can also do face grooving at the same time. As I said, face grooving now, the same code you can use G74 face grooving. Retraction, first line for G74R is retraction. The second one, X is where I'm grooving to right position. Then Z minus, where I'm starting to groove with a depth of, because this is a depth, I can split it maybe, first of all, 2,000 like that, 2,000 like that, but I'm putting it for just demonstration. Then here, that is 6,000 divided by 1,000, I get 6 millimeter. That's the depth or the peg. Then here, I'm putting each peg, I'm putting 0.3 millimeter with a filter of 0.1. You can also do part of, an example of part of. Part of, you can just use G01 for part of. So for part of, where am I going to part of? This is the point, maybe the safety, and then I'm going to a minus 80. From minus 80, I use G01, X to 0. I can put here X minus 0, 0.2 or 0.2, and this it leaves a material. But if I put X minus 0.2, it will remove the material completely. But I'm putting X 0.2, it leaves a material so the workpiece can hang, then I can just break it easily. Then filtered of 0.04 for cut part off. Then move away to a safe point. Then from there, go now to a rapid positioning where it's a safety. So as I said, a part program consists of safety approach, which is here, the cutting safety. This is the safety approach. Then this is the cutting. You see the cutting program. Then retraction, safety, retraction. So it has three parts. Normally, for you, consider using if your machine allows you to use G21 for metric, use G21, because G21 is normally for metric, then G20 for inches. So look at the program when you're initiating the program. For example, here we have initiated by G21, which means my machine it allows me to use G21 as metric. But if you want to use G20 for inches, now you put the inches. Then you need to also to configure the parameters over there. They're different. Then G40, we are cancelling any tool nose radius compensation. In case of any tool nose radius compensation, I cancel it. Then you have G99. I can set my spindle speed to revolution per minute, which means this is standard for turning. Others use G94 or G95. And then tool number. This is offset. Normally, tool offset, tool number, and tool offset. But for Siemens, they normally use T1, T1. Then M30 is the end of the program. Then save point. Always ensure that you go to a save point or home for purpose of checking the parameters. So this is for example for grooving. Maybe to finalize all the key areas that you need to understand is always check which code suits you when you're doing threading. Either you can use G32, G33, G76 or G92. Then ensure that the parameter is well explained, the pitch is well explained or commonly or properly selected depending on what you are doing. And then also if you are doing grooving, check the right code for or the right format for each of them or one of them. If you are using G74 or G75, then synchronize the speed as recommended from the chart so that you follow the correct sheet. Also ensure that you follow the right formula for calculating the depth, the depth, and also the major diameter and minor diameter. For the thread, normally the depth you take major diameter minus minor diameter divided by 2. Then for thread engagement, you can take 75% of the thread height for the strength, so that you ensure you improve the strength. Cutting speed, you can take for RPM, you take the surface cutting speed times 1000 over pi times the diameter of the workpiece. So this is the formula you can use to calculate the cutting spindle speed. The cutting speed, CS. This is the cutting speed formula. You can use it to calculate cutting speed formula. Or either RPM or CS. Then the feed formula also you can use this. The feed is normally the feed you take RPM times the feed per revolution. You can get now the feed when you are programming. So this is a summary key point. You can use it for your controller like Fanuc or Siemens. But the current Siemens machine are using cycle. For example, if you are doing threading in Siemens 840, use cycle 97. But if you're using others can use G331 or G332 for tapping. If you're doing tapping, so they may be different. Don't mix the code unless you have checked the manual that machine or the controller allows you to use the code as it is required. Always verify. In case you have a doubt of programming, always use a CAM package. You can use Mastercam, Vision 360, GipsCam, HCam, Esprit. You can use CamWorks, SolidCam, all of them. They can help you to synchronize the program as per the post processor. Before you send the program to the machine, it may allow you to verify the program first, customize the program, and even do a simulation to see how it will be cutting or behaving before you take a program to your machine. Key areas to understand that this guide is for training purposes. Also, it is for machining purposes because it's a complete guide for threading. No, I may not say complete guide, but it's an SOP for threading. Test the program. Anytime you write a new program, test the program first. You can use auto mode or single mode before you auto run the program to cut. Verify that all the calculations are running before you actual production or actual machining. Ensure that you use proper PPE. Your safety is very important, and ensure that your emergency stop is accessible and is working. This is how you will ensure that you write a clear program when you're using Siemens machines. In the next episode, we'll go to these are various examples. We'll use an example to write a program for our case. Yes, let me check. We can write a program for our case. A program, so we learn how to write a program for CNC turning. So in the next episode, I'll guide you how to write a program for CNC turning. For example, you can use this drawing to write a program for CNC turning.